if you have normally distributed data, then you can use parametric correlations. However, a lot of the time you're not going to have collected normally distributed data along both the x and y axis of your particular chart, because you're going to have picked specific values of the x-axis to measure the y. So testing for normality doesn't make any sense in those particular cases along at least one of the axes. But if you think that your data would be normally distributed if you sampled correctly, then you can use the parametric version. So Spearman's applies to all data, parametric and non-parametric, but if you think your data is going to be parametric, then you can use Pearson's product moment correlation. So the null hypothesis is exactly the same as with Spearman. There's no correlation between variables 1 and 2. The alternative is there is a correlation between variable 1 and 2 in the population that the samples are taken from. Now, this method depends on you calculating some things which are called the sums of the squares of the differences. So what you're looking at is the sum of the squares of x equals the sum of all the values of x squared minus the sum of each of the values of x squared divided by n, how many pairs of variables you have. The sum of the squares of y is exactly the same, but it's the sum of all the y's squared minus the sum of each of the individual y squared divided by n. And then you've got the sum of the product xy, which is the x and the y, and its corresponding y multiplied by each other, added together, minus the sum of all the x's times the sum of all the y's divided by n. Then you put that into the R formula, so R equals the sum of the products xy divided by the square root of the sum of the squares of x times the sum of the squares of y. Then you can test if this is significant by looking at the sample size and the degrees of freedom and looking them up in tables. Degrees of freedom are given by n minus 2. So in this case, in the case of the chickens, I had 13, so it will be 11 degrees of freedom. And then you can decide whether you accept or reject the null hypothesis. So looking at the same set of data as we had for the Spearman's rank correlation, assuming it's normally distributed in x and y, you can see that the sum of x is 161, the sum of y is 47.3, the sum of xy is 661, the sum of x squared is 25,985.44, the sum of y squared is 2,237.9, the mean of x, which we don't need in this case, and mean of y are there, and the sum of the squares of x is 2,153.8, and the sum of y squared is 208.35, and n equals 13. So you can feed all of those numbers into the particular equation. So 2,153.88 minus 25,000 divided by 30. These are complicated calculations, and it's difficult for people to do these multiple step calculations without making errors. In the past, when I've got people to do these from having a table of data like that and just using calculators, the number of people who've actually got the questions right using correlation is very low. Using SPSS or using Excel or just using any computational method makes this labor-intensive calculation trivial and much easier. So I'm never expecting you to do it in this formulaic way. But after doing all that, we end up with R equals 74.48 divided by the square root of 155 times 36.25, which happens to be 0.99361. That is slightly larger than the 0.98 that we got for Spearman's, saying that if I use the Pearson's, I've got an even stronger correlation between the amount of supplementers being eaten and the egg hardness. For 11 degrees of freedom, the p-value of 0.001, I would need a correlation bigger than 0.684. It is 0.99361, so this is an incredibly strong connection between the egg hardness and the amount of food supplement. It is way below the 0.0001 level, and in SPSS it's going to report it as 0. There's no chance at all that these two things are not correlated to each other. One final thing that I need to talk about in terms of the R's and Pearson's is, if you square the R values from Pearson and then convert it into a percentage by multiplying by 100, that's called the coefficient of determination. So this tells you what amount of the variation of the variable which is in Y is predicted by the variation of X. 100% is a perfect fit if you have a correlation of 1. This helps you to understand if you've got the most important variable for determining Y, or if the variable you've picked for your X is just a minor contributing factor. So if you found out that your coefficient of determination was, let's say, 10%, you know that 90% is coming from some other factors that you've not built into your existing model. So you need to go and consider what other variables might be contributing. And one thing that I'm going to mention now is you can also look at Pearson correlation and R in terms of effect size. So if your R is between 0 and 0.1, it's really insignificant. There is a relationship between the two. It might be even significant by a p-test if you've got a large as a p-value if you've got a large enough sample, but in reality it doesn't matter. Between 0.1 and 0.3 it's small. Between 0.3 and 0.8 it's medium, and above 0.8 this is large. So in the case of the pullets and the feed and egg hardness, it is extremely large. So if you want to look at an app which shows you different values of correlations and how strong your correlation is, so what a correlation of 0.6 or 0.7 or 0.5 or 0.9, how strong they look and how big the scatter is and how strong the line looks through them, then there's an app here that you can use to see how it varies.